Newton G. So what do you remember, guys? So that I will know where to start. What was the main point?
You were ignoring a certain interaction
Uh-huh.
that I'm having trouble remembering.
Okay. Correlation energy. That sounds like electronic problem.
Yeah,
I don't think we started yet electronic problem.
we were looking at what the Born-Oppenheimer ignored.
Oh, good. You remember we worked with Born-Oppenheimer, right? So what's the main idea behind Born-Oppenheimer? Say it again? Are they? Are they? Electrons and nuclei in molecules, are they separable? What does that even mean, separable? Well, remember I told you once about the separable operators, right? What was it about? About time-dependent Schrödinger equation, right? So in time-dependent Schrödinger equation we had space and time separated because the operator that you can write, d over dt, that operator, if h only depends on x, then you can call this operator a of x plus this operator b of t, right? And then you can write the psi xt as a product, right? Phi of x, t of t, right? So separable operators, that means this is an operator that is separable, right? It's the sum of two. One depends on one variable, another depends on another variable. This is separable. Now, for molecules, do have a separable case. What is our Hamiltonian? The electrons, nuclei, right? Molecules. You should be familiar with molecules at this point, right? You're chemists. So what do we have in a Hamiltonian for molecules?
Kinetic energy electrons,
Nuclei, yeah. Uh-huh. Right. So electrons, nuclei, nuclear kinetic energy. So these two, if they would form the operator, that will be a separable operator because these differentiate electrons, these differentiate nuclear coordinates, right? Everyone follows?
And so that T is the kinetic energy of many electrons all in one.
That's right. So to be specific, we can write I goes from 1 to number of electrons in the system, and then we have a Laplacian operator for every one of them with h bar squared 2m of electron. That's the precise definition, and then Laplacian for every electron is d2 dx I squared plus d2 dy I squared plus d2 dz I squared, right? So looks complicated, but yeah, it's not that bad because we don't have terms which would contain derivatives of electrons, say, with respect to x times derivative with respect to big X, and I usually use Greek subscript for nuclei, right? So we don't have terms like that. That means
Is that delta should be like, is that delta supposed to be the other way?
The Laplacian means the second order. This means the second order.
Oh, really? Oh, okay.
yeah,
They're the same thing?
yeah.
Ah,
The crazy story about this, there is this great Russian physicist Landau, and so he got Nobel Prize. So, and in many respects, he's like a size of Einstein, or at least in Russia. And so he had these tests for his students. Like essentially, if you want to work in his group, you need to go over all the tests. And there were 2 in maths, and then there were several in physics. And essentially, if you know Landau-Lifshitz book, there are 10 volumes, and of that kind of for every aspect of physics. And so essentially, every test was on each separate volume. Right, and the problems were quite standard, so he didn't change them. And even his students start to kind of joke on him and playing jokes, and they prepared a person from humanity, right, to pass through the test because they knew what the problems are, and people from humanity, they have good memory. So the only thing that go confused was Nabla from Delta. And that's how they kind of saw that she didn't really understand anything what she was writing. So anyway, so this operator is very simple, and Laplacian Nabla squared is the kinetic energy differential operator that is there. So there are no cross terms, and but the trouble is coming from the potential energy part, right? So there is electron nuclear plus D and N. And so this is the guy that connects, that binds the molecule together, right? Coulomb attraction between electrons and nuclei. So DEN, Z of electrons, or Z of nuclei, and then you have Ri minus R alpha. So this is a distance between position of electron and position of particular nucleus, and then there is a sum over all electrons and all nuclei. Okay, so this is a strong term, it binds, and then we cannot ignore it, we cannot make a product ansatz without considering it. And so what we introduced was that we're going to split the problem still, because we don't want to solve for both for electrons and for the nuclei together. So, but we will split in a smart way where there will be electronic Hamiltonian that consists of everything H minus Tn, right? And then the total Hamiltonian is nuclear kinetic energy plus electronic Hamiltonian, right? And so the solutions for electronic problem, probably Jessica will tell us about in her lecture, and how we solve electronic problem, because electronic problem is difficult since the electrons are quantum particles, the most quantum in the whole molecule. Nuclei are heavier and can be treated in many cases classically. So, but the electrons cannot be treated classically, and that's why, and then plus they are indistinguishable, lots of complications. But at least we fix nuclei in this problem, and then we can obtain, this is just a reminder what I was finishing my lecture last time. All right, so we got the eigenvalue problem. And then once we solve this, we can write, if we are interested in, say, dynamics, say photosynthesis or photochemistry, when you have a molecule, you shine a light, and then you see some chemical reactions or physical kind of processes of energy transfer. One of them is like right in front of your eyes. We all see because there is a energy transfer from light to proteins in our eyes, rhodopsin, which has a small molecule retinal, and then retinal undergoes this conformation transitions from 11 cis to kind of all trans. So the say this terms, yeah, this term E electronic energies that are also functions of nuclear parameters, right? So if you have
so that's the Hamiltonian of the electron and then the energies, like on the left hand side is the Hamiltonian, the right hand side is the energies?
that's right, yeah. So that's the electronic problem. On the fixed nuclei, they became parameters, and then we solve the eigenvalue problem with the functions that are dependent only on electronic variables, right? So the only variables here are the electronic variables. The big R's, the nuclei, they are fixed at every, like we fixed nuclei, and then we solve the problem, we get some values, then we shift in nuclei, right? So we got different geometry, and the case I was about to show you was about this 11 cis is carbon-carbon double bond, hydrogen, R prime. So there is this fragment where R and R prime, they are not nuclei or variables stick to the molecule, but rather radicals, which can be some other molecular fragments like CH3 or other conglomerates of atoms, essentially, right? I don't specify them because I simply don't remember what is in retinal. It's a big molecule, and then but there are some fragments essentially. And what happens is that in this large protein there is this fragment. The bonds are arranged like this, and that arrangement consists the lowest energy, and then if you start rotating, for example, R and R prime, this is a dihedral angle essentially between them, right? So if you if this is R and this is R prime, so then you start changing the dihedral angle, rotating, and say this R is this dihedral angle, phi, and then naturally, since it's a minimum, the energy will go up. The electronic energy. We're talking about electronic energy. If you keep solving this electronic Hamiltonian eigenvalue problem, then these energies for a ground state, the lowest energy will go up when you start changing the conformation, right? So, but this barrier essentially separates us from the state, the dark state, when we don't see anything. You close your eyes, you are here, and when you open your eyes, light comes in. There is an excitation from the lowest state to the next state. In chemistry, they're called S0 and S1 for a reason that the spin symmetry is singlet for both states. We didn't talk about spin yet, but yeah, let's just consider this as labels. Okay, so then you do the excitation, and these energies, even just using the simple kind of classical intuition that nuclei are moving classically on then these potential energy surfaces, and you can see that they would just go down and eventually end up here, because the force is the derivative of the potential with respect to the dihedral angle in this case, and so they go down and end up here. So that's the first step in the vision process. Okay. Now, why does this happen? What really happens? How do we now, on the more formal level, how do we understand this process? Because at this point, it's probably clear for you where do these curves come from, right? Because our electronic energy eigenvalues, right? They depend on the nuclear parameters. right? So then, and there are many of them. So we naturally get curves, or they are curves because I'm using board. And if, well, in real life, the R is the nuclear degrees of freedom. There are 3n minus 6, where n is a number of atoms, right? So those become surfaces, right? Because you have energy as a function of various nuclear parameters, right? And then there are many of them. That's why you have several surfaces. And now, how do we understand the dynamics, or the chemistry, or photochemistry in this case? It follows from solving the time-dependent Schrödinger equation for the total wave function. And the total wave function in this particular case would be the chi1 term, depending on nuclear and time, right? And it's written in this electronic basis. So note that the basis is static, right? Nothing is changing. Since to get this basis, to get these functions of R, small r's, we fix nuclei and we solve for the electrons, right? So there is no dynamics here. Dynamics comes later when we define the total wave function in the following form. Now,
And that's the wave function for the whole system, that product?
that's the sum of products. Okay, one product would be a Born-Oppenheimer. Right? One product means that we're considering the surface that is not in any way connected with anything else, with any other surface, right? So that gives us potential for that particular surface, function of R, and then that's just a one product. And if you'd like, we can consider one product first. Then what you get is H is Tn plus this energy, right? And when you put this into time-dependent Schrödinger equation, what you get is okay, so Tn plus E of R, that then acts on, say we're working with one product, chi phi, and then it is equal to I d over dt, and we put the same product, chi phi, right? So what happens here, since only our chi depends on time, right? So we do not differentiate phi, we only differentiate chi, and also we can integrate out the electronic variables from this equation if we assume Born-Oppenheimer approximation. So we do the dr phi from the left, right, acting Tn plus E of R. What do we get? We get, well, these terms. Right, then they become just Tn because of the Born-Oppenheimer.
What happened to the chi?
I'm just saying that the Tn operator dressed with these phi terms still Tn operator, right? And then we will get to the chi in a moment. So, and then phi star E of R phi is just E of R, right? Because E of R is a function of big r's, we're integrating over small r's, and these guys are orthogonal or orthonormal, right? Yeah, you have a question?
How come chi isn't affected by the kinetic energy of the nucleus operator?
Where did you get that?
Right? Well,
Where did you get that? So this is the last statement about the whole thing, right? What I'm doing, I'm projecting from the left this equation with this operator. Essentially, I'm acting with this operator on the whole equation, right? And then to do that, what I do first is I'm simplifying, and there will be term that phi, Tn, phi, and then that whole thing will act on chi. Okay? So I'm just saying, okay, there will be this instead of Tn, right? Because you integrate in phi. Say you decided to integrate phi first.
Yeah.
Okay? And then
nothing
nothing prevents you to do that. Right? So you integrate the small r first, and then whatever will be your operators, you will act with these operators on chi. Right? So that's just a two-step procedure. Okay, and then it's just simply that way. Then what you get is Tn from here plus E of r from here. Right? This, the only thing that is left is chi. Right? Because phi sandwich Tn get us Tn. Phi sandwich ER got us ER. And then the chi is only left. So this thing acts on chi. And then what we have here is, again, phi will disappear because this part doesn't depend on small r's. And so what you got is, this is our Schrödinger equation for the chi part that carries the dynamics. So if you have some surface, then you have some initial chi function, then it will move according to this equation. Okay? So and that's not any different than just, say, particle in a box or harmonic oscillator. Depending on E of r actually is closer to harmonic. I guess in most of the molecular applications, E of r looks like this. Right? So if you have a chi r0, like a ground state harmonic oscillator function, then it will stay that way. Okay? So nothing will happen. But if you say build the chi of r0 as linear combination C1 harmonic oscillator function, or chi harmonic oscillator 1 plus C2 chi harmonic oscillator 2, right? So it's a superposition of, this is a ground state and this is an excited state of a harmonic oscillator with some coefficients, and that would correspond, since this ground state is asymmetric. Next is the antisymmetric function, and if you sum them together, say with the same coefficients, divide by square root of 2, you'll get something on one side of that well, and that wave packet will just be moving back and forth on that parabola. Okay, according to time-dependent Schrödinger equation. This one, right? So everyone sees that if, say, we reduce this is a bad seat you choose. So if this will be just a second derivative with respect to x, and this one will be the kx squared divided by 2, which is a harmonic oscillator potential, and this is just a time-dependent equation for harmonic oscillator, right? And then you can see, you can model the motion of that wave packet on the parabola, and but that's just one particular electronic state we're considering here, right? In case of rhodopsin, retinal, what happens is that when you excite, you have involvement of both ground and excited states. Why? Because you start at the ground state and then you excite to the first excited state, electronic excited state. So these E's that are involved first and second. This one corresponds to S0, this corresponds to S1. Okay? And then, as you can see, everything ends up on the ground state, right? So eventually, because what happens is energy transfer. Sun gave us energy for the photons. They came to our eyes, and then we can see. right? So that's the process, because you can think now of chi corresponding to the ground state, chi 1. Then we excite with a sun, light, or photon electromagnetic field. We obtain the chi on the excited state, and that wave packet just slide it through the region of so-called conical intersections. We'll get to that, and essentially end up on the ground state. So the population would be transferring between chi 1, chi 2, and then back to chi 1. Okay? And the total process can be represented with this construction, right? As I was saying, the chi 1 is the time-dependent nuclear component corresponding to ground state. Then if we start dynamics having the initial conditions that, I'll say the light usually is considered to be very fast, right? So then you excite system on the excited state and let it go, and eventually it will end up on the ground state. But in quantum mechanics you have, of course, both ground and excited state in some ratio. Of course, the majority of the system will be in the excited state. Okay, so if you calculate probability to find system on the excited state or in the ground state, here it will be higher than the probability on the ground state. All right.
So these surfaces that we're jumping between they're surfaces of potential energy, right?
That's right.
Okay.
Right. And within those surfaces, we can solve equations for the total electron nuclear dynamics. Okay.
And they've got to be real values because of potential energy?
Because the operator for which we're solving this equation is a Hermitian operator.
Okay.
Right? So any Hermitian operator has real eigenvalues.
Yeah.
Right? So electronic Hamiltonian is Hermitian. That's why all our energies are real. Which is good, yeah. And then this problem naturally split in two pieces. The electronic, which may seem to be static, right? So you may say, okay, you are talking about all these excitations going from the ground to the excited electronic state. So it looks like electrons are participating. The state is changing. Why the electronic but there is no time dependence in electronic functions. Yeah?
Is it because we made the Born-Oppenheimer approximate, like we took out a term? Or my other guess is we have a linear combination, so you get these cross terms?
Well, technically you need to clarify what do I mean by participation of particular variables in dynamics, right? So what does that even mean? How do you say you have a wave function that contains both? Clearly it contains both the nuclear variables, electronic variables, and time. How do we figure out which subsystems are participating in dynamics? We need to get rid of others, right? So, and the way to get rid of, say, nuclei in this problem is just to integrate them out. So if you have a wave function psi, right, then you can kind of write down things in some nuclear bases and integrate. I'll say you create some bases depending on the R's, right? And then you integrate them. What will you get? And this is kind of some basis. Right? Then you will have some electronic functions which will depend on the small r's and t. right, that will describe how the electrons are evolving, because they will depend both on the electronic variables and the time. So in a sense, how does this time dependence come into play? Because every electronic function is multiplied by this prefactor, right? And naturally, because these things are changing, you can say, okay, if say the integral of chi1 squared over dr is close to 1, that means it's almost 100% probability to find our quantum system in this electronic state. But of course, overall probability is 1, so that means the corresponding chi2 squared dr will be close to 0, right? And then if you study processes that are involving interchange of the population between the one electronic state and another electronic state, then you can say that you can monitor these norms for the chi parts, and this will be probabilities of finding electronic subsystem either in a ground or excited state. Okay? Because in order to, well, how do we, this is a complex object, right? And how do we find the probability to find system on electronic state 1? There should be an operator to answer that question. What is the operator? Any idea?
I'm not even exactly sure what we're trying to do.
Say if someone gave you a function psi, right, that is written in this way,
Yes.
right? So the question is, what's the probability to find electrons in the state that is described by these functions?
The inner product?
Right, but inner product between what?
So the psi, what would that be as an operator though? Like the thing that we're looking for is phi sub E1, right? That's what you're saying we want to know.
Well, in any quantum, like if you want to obtain any property, right, in the quantum mechanics, then you need to have an operator corresponding to that property. And so if we are talking about probability to find system in electronic state number 1 or electronic state number 2, there should be an operator that eigenvalues of those operators would be the kind of resultant probabilities, right?
Yeah.
So the question is, what is the operator? And the operator, I already gave you an answer what we're looking for in the sense of that the answer for the probability question should be either this or that, depending on whether we're looking for probability to be in state 1 or state 2, right? But how to formulate the operator? It's actually not so difficult. It's just, say, probability to find system in the electronic state number 1 is this projection operator. All right, and then correspondingly projection on the second state will be a.
That's not an X email. I finally remember.
That's right. Yeah. So it's a bracket, right, notation. And then if we use those projectors, then with the total wave function, right, the probability, average probability because the function itself is not an eigenfunction, right? So then if we measure, then we'll get different values every time, but the average of that distribution will be given by this expression. And if we introduce this projection operator, right, then we'll have, say, for the first state, right? And here, because we would like to get number, we need to integrate over small r's and large r's, right? Otherwise, if it's only small r's we're integrating, or all big r's we're integrating, then the other variable in psi will be there and we'll get functions. It's fine to get functions of t, right? Because your averages can vary with time, but it's not appropriate to get the functions of spatial variables if you're looking for probabilities to find system in a particular state. So then this becomes just an integral over dr, d big R. The one side here is sum over chi I phi I e. That's just the psi, right? That's the first integral. And then the second integral is the same, but just up to conjugation and right, and variables could be called with primes, right? And then the phi e1 will be conjugated, and the total wave function is not. And again, using the fact that the integral over small r for the phi I e, phi e1 is delta I1, right? It's Kronecker delta I1, right? Then the only term which is going to be left here is the chi term. And I think I made a mistake. Do you guys see where I made a mistake? The big R integral is one integral over the whole thing. Okay?
Isn't that okay the way that you wrote that? You're not.
Oh, I introduced two dr big R's, right? And actually that should be only one.
Oh, one of the whole.
Right.
Oh.
Right, because that's tricky, because this projector, it has two different integration over small variable r, but only one, because it's, after all, what we're doing here is these brackets are integrating over small r and big R. And then what happens here is, if we go and represent this projection operator, that's an integral operator in the small r space. So then there is another small r integral there. And then what we're getting eventually is only one chi suffice that corresponds to the ground electronic state, and then big R chi 1 with the star, and chi 1 from this integral without star. All right, this is chi 1. Right, so that's the probability. Yeah.
So sometimes when we put in that kind of like ket bra, it's just equal to the identity. How do we know when it's not equal to that? Because clearly this isn't just one.
Good question. So the way this can be done in a somewhat clear way, fashion is that we can introduce, since here we're talking about functions of electronic variables, right?
Mm-hmm.
So what is the nuclear component here? And one way to address this nuclear component would be to say, all right, actually what we mean is there's electronic function in electronic subspace times the resolution of identity in the nuclear subspace. Okay? So essentially, this part is projecting on the first electronic state, but this one, the actual nuclear component, doesn't do anything. It just stays there, right? Because you have a space of two variables, small r and big R, right? You cannot, if you are formulating an operator, then any operator, say differentiation with respect to x, right? If you have a function y, right? So what you can say is that you're actually working with the operator that has identity with y, right? Doesn't do anything in y. Okay, and so then it will identity in R. You can even write it as in the configurational space as delta functions, and then you can have two big R integrals. One will just be integrating the delta functions, and eventually you will get only one big R integral because you made the resolution of identity with the position eigenstates, right? Yeah, it's a good idea or good suggestion in the sense that to work out the details, I think it would be nice to put it in the homework to essentially repeat all this in the using the spatial representation for the projection operator that will put everything in place. Because here I introduced this in a kind of Bryan-Ket notation and then eventually did this using the coordinate representation. Okay, but once we have a wave function, which we, well, for two states, if we obtain the kind of non-Born-Oppenheimer dynamics full without doing the Born-Oppenheimer approximation, then we can decide or study the question how much of our system is in one electronic state versus another. Okay. Seems like you're excited about this.
Sorry, migraine.
Migraine. All right. Time for break. Okay, time for movie. Why don't I set up movie and or you can go to the break and come back and I will show you the movie about how this actually works on a computer on some simple model. Okay. Show you is these chi functions. They will be red and blue, corresponding to different electronic states, and potential energy surfaces are the ones that are depicted here in black. Two parabolas, they are crossing, and so at the point of the intersection there is the best transfer, and oops, yeah, it's dying anyway. So
what are the two black lines?
potential energy surfaces, right? So you have E1 as function of R, where R is just x, right? E2 as a function of R, right? So they form two parabolas. And we plot in the chi functions, and we start at the, say, left parabola, right? And then we move in, because we're starting on the slope of the parabola, so it's in a kind of a coherent state of harmonic oscillator basis functions. Then it will be moving, and if we do not have coupling terms, then it would just keep moving on a parabola. Okay? And so that's the first dynamics I wanted to show you, is that it's kind of Born-Oppenheimer style dynamics where, let's say, this is a ground state, the left parabola, and then it's just the chi1 that is participating in the whole dynamics. The blue line is flat, the chi2 is 0, nothing happens, no transition essentially, right? So it's just coherent oscillations back and forth, nothing interesting. Now I add the coupling between the two terms, and we will have some action and transfer of the population between the two states. Just a second. Stop. All right, so if we make small coupling, then there is something on here. You see, when we come to the intersection, this blue line acquires some shape, and whenever red wave packet comes close to the crossing point, then there is a enhancement of the transfer. Yeah, so the blue curve gets more and more population. So
blue is the nuclei?
both red and blue. The red is chi1 function of r time, and the blue is chi2 rt. Yeah. So whenever you have interaction between surfaces through non-adiabatic terms, then you get the transfer of the population. And so when we didn't have coupling, then only chi1 was significant, so it was non-zero, and then the blue was 0. But once we added to transfer terms or coupling terms, then we start getting something in blue. And here's the strong coupling case, where the transfer happens even before reaching the intersection region. And so you can see the blue becomes comparable to the red. If you, of course, integrate and square, that will be the probability to find a system in first and the second states. Okay? But that's what you can do for the 1D problems to visualize this dynamics. Okay? Yeah.
This may be kind of a silly question, but why are they parabolic?
Because I made them parabolic. Okay, so you can play with these potential energy surfaces the way you'd like. Technically, they are coming from electronic structure problem, right? So you fix nuclei for real molecule, and then you obtain some curves. And so if we look at the diatomic, say hydrogen, right? So the simple diatomic molecule, then there is an equilibrium distance that corresponds to the minimum of energy, and then beyond that minimum, it's more like a Morse curve, right? So, but for the simplicity, you can always keep it parabolic, right? If that would correspond to the case where you consider in dynamics not too far from the equilibrium position, right? And
So this is moving in time, right?
that's right.
So if we say let it run for an infinite amount of time, would there be like say basically
Yeah, I kind of see where you're going with that. Maybe. But this is a finite kind of dimensional dynamics, so in a sense we have only one degree of freedom. And so what's going to happen if we keep going is that population will go from one state to another, and then will come back, and then go again, and so on and so forth. So there will be oscillations, not within one parabola, but within two parabolas, right? And you can also think about this problem by diagonalizing the whole Hamiltonian. So you can have now two parabolas that corresponds to two electronic states. The Hamiltonian of this whole problem is H11, H12, H21, H22. Those are the electronic blocks. And within those electronic blocks, we have also vibrational functions, right? So our kind of total representation of psi can be written as a sum over Cij chi I phi j, right? So I'm talking here now not about adiabatic states where we only need two states, but in terms of kind of just a general basis, right? So chi will depend on the nuclear variables, and phi will depend on electronic variables. And since I'm not considering any real molecule, the electronic variables will be just state 1 and state 2. I just selected them that way. And then I will have the Hamiltonian that I can diagonalize. I can get the eigenstates and eigenfunctions. And then there will be, well, oscillations between the states of, if you think about this in terms of these states, the states before diagonalization, right? Then you can think of initial wave packet given, well, some coefficients initially, and then the coefficients will evolve, and you can monitor dynamics in terms of these coefficients. But the physical picture will be in the coordinate representation like I showed you here. So it will be just going back and forth between the two parabolas, right? If you have a situation where there are more nuclear degrees of freedom, what you would expect is some kind of approaching equilibrium, right? So that means the parabola which is higher in energy, you starting from there, and you would be in some kind of Boltzmann distribution rather than a wave function, right? And then they will be transferred to the lower parabola back and forth, maybe for a couple of cycles, and then eventually you end up with a Boltzmann distribution, kind of for the overall system. Okay, so you start with non-equilibrium distribution and you end up in the equilibrium. So statistics wins after all. That's why it works. That's why if you are working with the long time scales, all these oscillations, interferences, they may not be that important. You eventually get to the equilibrium, and well, for us equilibrium means death, right? So from our perspective, all this vibration, that's life. That's interesting. But once you're in a stationary state, then there's nothing to worry about anymore. Okay, so that's the movie I wanted to show you, just to illustrate how this can be done. And we'll talk a little bit, maybe closer to the end, if we'll have time, how to do the real simulations, and so that you can try it at home on a MATLAB. MATLAB is a very powerful program. I really like it because it has visualization and solving simple linear algebra problems in numerically efficient way. It's very easy there. So doing dynamics is it's just a perfect package to do the dynamics for model systems. Okay, now let's consider non-adiabatic terms, the ones that are driving dynamics between ground and excited state, because what I would like to show you is when these terms become large and when they are small. So when do we expect deviation from the Born-Oppenheimer approximation, and when using the Born-Oppenheimer approximation is fine, right? So let me remind you that the way these terms appear are through action of Tn on electronic functions, right? So we have this type of terms when we project the total Hamiltonian, this equation, say, onto the electronic functions, right? And what I did here was a Born-Oppenheimer approximation, right? Because if we have more than one phi, even if we have just one phi, it depends on the electronic variables and the nuclear parameters, right? And this operator differentiates the nuclear parameters, right? So technically, we cannot ignore the differentiation of big R's in this expression, okay? And so we need to apply the chain rule and have several terms. So if we have, for simplicity, let's say we have 1 degree of freedom, big R, right? So we have d squared dr squared, and it acts on the phi I R, right? And then what we get is, well, the simplest term is when we just differentiate phi and nothing else, right? So if it's easier just to consider this with some chi function associated with phi, then the first term is this. Then we'll have terms where d over dr is acting on the phi, and d over dr is acting on chi. Plus we'll have a term that appears in Born-Oppenheimer, phi I. Okay? Is this clear? Is it clear? Oh. Huh? It's a chain rule, that's right, yeah. So in Born-Oppenheimer, we neglected this term and that term. Well, both terms contain differentiation of the electronic function, right? And now we are about to see when these terms are important. Okay, in order to see that, it's easier to work in Bryan-Ket notation, and in the Bryan-Ket notation we will integrate only the electronic variables, because the terms that will appear, so-called non-adiabatic terms, which are appearing, so phi I. No. Again, for simplicity, I can just put d over dr, phi j, d over dr, and then since this whole thing comes from the momentum, there's this part multiplied by 2, and we integrate only the small r variables, right? So for this term to be important, this part must be large, okay? And the second derivative terms are like this. And we have minus h squared divided by 2m. Well, first of all, m's are involved here, so they're divided by large masses, right? But so is just a normal kinetic energy, right? In normal kinetic energy, you have large masses of nuclei, and so mass alone is not giving you rights to just discard these terms, okay? Then the algebra that is kind of revealing here is the following. So if we say consider this phi I electronic Hamiltonian phi j, okay? So if I and j are different, what will be this term? It is 0. Why? Because phi j is an eigenfunction, phi I is an eigenfunction, H electronic can act either here or there. It will produce essentially energy, either I or j, and then it will leave us with phi I, phi j, that is a Kronecker delta, right? That's why it's 0. Okay, good. Now, we want to get to this from here. How do we do that? Here's the way. Let's differentiate this with respect to big R. Okay? And so we have, again, chain rule, because this, and this, all terms depends on big R. So we need to differentiate all of them. All right, so this derivative plus this plus this, right? Now, one simplification is that this term and this term, we still have electronic Hamiltonian, and phi I and phi j are still eigenfunctions, right? So we can act with electronic Hamiltonian here on phi j, here with electronic Hamiltonian on phi I. You had a question?
I was wondering if they cancel or not. Like the first one, the third.
Not anymore, because we differentiated, right? We differentiated functions, right? So, but bear with me. So what we got is phi, after accounting for the fact that Hamiltonian is acting and producing energies for us. Here it will be j. And here, let's consider first and third term first, and then we'll get to the second one. With second, nothing can be done. Okay, so it will stay the way it is. And then with the third one, it will be d phi j dr ei, all right? So plus second term. And then, since we differentiated something that is equal to 0, we cannot get anything but 0, right? So no matter how many times you differentiate 0, then you still get 0. Yeah, that's a nice thing about 0. Okay, so what did we achieve? We achieved the following thing, is that this anymore not 0, and the second term is not 0, so essentially we got 0 split into 3 terms, none of which is 0. Right? But the nice part about these 3 terms, seems like we increased the number of our problems, but the nice thing about this part is that the second term of this expression now looks like this term that we're interested in. Okay? And I will show you, it's very simple, how this can be also expressed as this. Yeah?
I was wondering, so the derivative operator is
Yeah.
skew Hermitian, right? So we can switch it.
That's right.
So we get an R sign?
Yeah. Is this a question, or?
Yeah, like if I was going to say, can we do that here?
Yeah, that's what I was about to do before you interrupted me. But that's fine.
But that took the assignment, right?
Was it?
Like I feel like, because
That is in step.
yeah, I was doing one of the questions and I was like, that's what we're doing right here.
Okay, yeah. Everything is related after all.
Yeah.
So,
Cool, so I did it right.
okay. All right, so now, but what Tyler said can be expressed in even, I think, simpler way, because this anti-hermeticity that you're talking about, it comes from the simple, again, differentiation of another zero. You can write this, right? This is 0. And you can differentiate it, d over dr, right? And so then what you get is d phi I over dr phi j plus the second term phi I d phi j over dr.
That's a much faster way to show it.
Yeah?
Than using integrals and in differentiation by part and throwing
Yeah.
away the boundary terms.
Yeah. Oh yeah. Plus, oh, I guess you.
With that question, could you have just assumed that they were normalized? And not this one.
Mhm.
The question in the assignment, could you just assume that they were normalized?
What is normalized?
You see, I'm teaching 2 courses, and I just finished the midterm with another, and I posted, I think, homeworks for you and for that class as well. So I don't exactly remember which assignment and which question you're talking about. Can we get to that after the lecture? Because yeah, so these are all related. Assuming normalization, assuming, well, what I assume here, or what I started with, is that this phi I, phi j basis is orthonormal, which it is, right? So it's electronic functions. So we know about them is that the phi I, phi j is delta ij. So we can do this, or we can start with I and j the same, so, and do the same algebra. Because in I equals j case, we would differentiate 1, and 1 will still be, well, after differentiation it will be 0, right? So the main idea is the same. Anyway, so that's what we have, and now we can simply write, since the sum is 0, then 1 is minus another, and that allows us to substitute this term with minus that term, right? But lucky for us, the energies are different, right? So then we don't get the cancellation, and what we get instead is some new insights. And the insight is the following. So that we have j, and then with minus, okay, so the j goes with minus, ei goes with plus, and then it's multiplied by phi I d phi j dr, right? And this is plus second term, which is phi I differentiated Hamiltonian, phi j, right, should be equal to 0. And then we can express this term that we were interested in, because that term is the one that is, well, one of the non-adiabatic terms, essentially, right? And so we can express it in terms of this too, right? Electronic, and then E j minus E I. So what does this tell us? That this term is inversely proportional to energy difference. Okay? And this is the main message here, because we assume that if we don't know much about the problem, it's kind of somewhat hard to estimate. At least I don't know easy way to estimate this term. There is kind of a symmetry argument you can use. We haven't considered symmetry much at this point, so I don't want to go there. But there is probably the cases where you can know in the symmetry of two functions and know in the symmetry of the coordinate that you are considering, you can say whether this integral is 0 or not, right? But apart from that, you can say that closer the energies, adiabatic energies are, I and j, larger this term will be. And so that is a main argument for saying that whenever your surfaces come close to each other, then non-adiabatic terms become important. Okay, so because the gap E I E j becomes small, and there are cases where actually they intersect. Okay, so then this term diverges to infinity, and you cannot ignore anymore the transition between states. Those cases we'll consider, they're called conical intersections. Conical intersections. When Ej equals to Ei. Okay, and then this term blows up to infinity. Okay, so that's the main hallmark of non-adiabatic dynamics, and in rhodopsin is one of the cases. There, what happens is that these two surfaces cross. That's why wave packet, when it travels on the kind of upper state, it eventually ends up on the lower state because there is no gap. So it can travel very quickly from the upper state to the lower state. Okay, so that's one of some people say that's one of the fastest dynamics in chemistry because it only takes 200 femtoseconds, although Dwayne Miller disagrees. And there are some arguments or I guess some experimental findings that say that it's actually even faster, right? So at least 200 femtoseconds would be, I guess, a more correct thing to say, which is very fast. Yeah. So, and that happens because potential energy surfaces come close to each other, and the non-adiabatic terms become large and super large, and then there is a transition of chi1 to chi2 or back. And kind of one way to think about this in a more intuitive way is that there is constant energy exchange between electronic and nuclear subsystem, right? And generally in normal Born-Oppenheimer, when the surfaces are far, electrons, they're kind of like a capacitor with a large amount of energy that can be stored, right? So light strikes and you excite system from the ground state to the excited state, and then there's lots of energy went into the electronic subspace or electronic wave function, right? Now the electronic cloud is very different, and to go back you need to deposit that energy somewhere. We have energy conservation always haunting us, and so how do we do that? The only like a normal way to proceed would be to transfer things to heat. Heat, that means vibrations, right? So you deposit it in vibrations and dissipate the energy. That's how sun blocks, sunscreen blocks work, right? So the sun hits and then UV light is essentially redeposited in vibrations. Yeah.
I was going to say, couldn't it release a photon?
Yeah, that's another way, but that is in a quantum electrodynamics domain, right? So quantum physics at this non-relativistic level doesn't have a tool to actually consider that process, right? So it would require creating a photon, fluorescence essentially, right? It would require you to have additional kind of vibrational degrees of freedom, but vibrational degrees of freedom of vacuum, right? And also virtual phonons creating the excitations in that area creates light essentially, right? So that's my naive understanding of what's going on in the quantum electrodynamics domain. I never studied it systematically, but essentially you can think of it as an additional reservoir or bath of the vibrations, and those vibrations are associated with creating light. You can quantize electromagnetic field into harmonic oscillators, and those harmonic oscillators will correspond to that extra environment, right? Yeah, and that's what essentially happens when you do not have regions where potential energy surfaces come close to each other. Why? Because it's a lot of energy to deposit into the normal vibrations, and that usually doesn't happen. What happens is that the process of fluorescence, and this energy is deposited into light, back into light, right? It came from light and back to light. But the fluorescence is so-called quenched, right? When there are regions in the potential energy surface where they come close to each other, right, the surfaces, and then non-adiabatic dynamics kicks in because the non-adiabatic terms become large, okay? And my kind of simple analogy would be that you always, in order for energy to transfer, you always need to have a resonance condition, right? And if the amount of energy is large, you need to have a reservoir that could accept that, right? So that's a simple example would be if you bounce a ball, right? It has a potential energy, then it goes to the kinetic energy, then it bounces. So this floor, for example, concrete floor, doesn't accept that energy really. It bounces back.
Okay.
But you cannot bounce ball on the sand, right? It will just receive, right? So why? Because sand can accept all that energy that you have in the ball on that height, right? But if you have this concrete floor, then it doesn't accept. Why? Because the vibrations of the atoms in the concrete floor or hardwood floor, they are much higher in energy, right? So they cannot be excited because of just some small ball, right? And there is a mismatch of energies, and that's why there is no effective energy transfer. Conical intersections, essentially, what they give us is the region where energy scale of electrons and energy scale of nuclei, they come close to each other, because the transitions between these two, say, points in the electronic domain is relatively small and comparable with the vibrational distances between the vibrational levels, right? And it can be as small as we want once we come close to the intersection. Okay, so now this is the first order couplings. Now there are also second order couplings. So what happens with those? Similar tricks can be essentially used with differentiation and resolution of identity. And there are ways to express second order couplings as product of the first order couplings. Okay. So the way it goes is following. So we can now focus on this. All right. And then what we can do is we can consider this as two operators, which second derivative is two differentiation, right? And we put here the resolution of identity over all the electronic states. Here we consider two particular I and j. Here we put the resolution of identity in the electronic subspace where we sum over all electronic states, potentially infinite. Okay, and of course in the normal applications we always have a finite summations, because other states, they are not really like the high up states, they are not really relevant for our physics. But nevertheless, there is a sum, and so then what we can write is following. Okay.
So because the phi k's, I'm just confused as to why at that time the other product is an identity, but it wasn't earlier. Is it because they're using the same function twice?
When was
When we put the projection operator in, it
right?
wasn't strictly an identity.
Because projection operator contained only one particular product of ket and bra, right? So when we were writing projection on the first electronic state, we were writing it like this. All right?
And we're not doing the entire sum.
That's right.
Is the identity.
Here we use entire sum, because entire sum forms the complete set, right? And then that's always a way to represent the identity, right? Here it's just one term. We are focused on the one particular electronic state, and this is a projection operator that allows us to see what's the probability to find, okay, in that state. Now here it's a whole sum, but this whole sum, every term depends on R, so we actually got ourselves into more troubles by doing this. Of course, we will gain something at the end, but essentially we will need to differentiate now. If we want to consider this operator, we need to differentiate with dr this term, and eventually it goes all the way and creates back and gives us back this term. And since we're differentiating identity, of course, we're not gaining anything by differentiating this and this, right? So sum will be still the same. But the algebra will be beneficial for us. And so what we get is here, of course, there is a summation over k. Summation over k, phi I, dr phi k, first term plus phi I, phi k, second term plus third term. All right. Okay, now this is ik, delta ik. This is delta ik. So k must be equal to I. So then what we have is phi I j equals to Okay, and then this term becomes this term okay at what these two terms given us, if we sum them together, is the following representation. We can see them as phi I d phi j, right? These two. And then the only thing which is left, so now you see we started with this term and we wrote it as a sum of this term, and we know already that this is proportional to 1 over ei minus ej, right? So derivative of that with respect to r will give us something like 1 over ei minus ej squared times some derivatives of is ij respect to r, right? So essentially this term will decay with the difference in energies even faster, right? Or grow even faster with I and j being close to each other. And then this term, what we can do with that term is just considering this sum, the k actually in this sum should not be equal neither to I or j. The terms where k is equal to I or j, they are zero terms. And I will, it's easy to show. I'll show it in a moment. Now, without those terms, we can again apply this logic that whenever we have a term where we differentiate one function, then we'll have our energy difference in denominators. So I df k dr k df j dr, and this is proportional to sum over k not equals I or j, and the energy difference between I minus k and 1 over ek minus ej, right? Now why the terms which are diagonal are zero? It's very easy to show. So if, say, you have an expression like this, where these two subscripts are both the same, okay, then this is 0 if fi is real. Okay. Now, why is this the case? We start with phi I equals 1. We differentiate it. Then it's 0, right? And then we consider that 0 as d phi I dr phi I plus phi I. No, again 0. So that means this equals to this with minus, and this is the integral where technically we're supposed to take the only difference between this integral and that integral is the conjugation, right? This is this integral, and this integral is integral over phi I star d phi I. Right? So if functions are real, then conjugation doesn't mean anything, or it's a kind of identity operator. Then this equals to minus itself, right? So the only number that satisfies that is 0. Right? Then this is 0. For that reason, we can neglect in this sum the case which are equal to I or J. Oh, we can always work with the real functions in this problem because Hamiltonian is real, right? So we can, based on the physics of the problem, we can always choose to work with the real functions. It's a good point that sometimes we can work with the complex functions, and then these diagonal terms are not 0 anymore, right? So then you would need to consider them and see what these values will be. But for the sake of this consideration, we can say, okay, we always work with real, and then this is just to show that in the real space we can always make these functions to be small, or these elements to be small, whenever the energy gap between I and J is large. Okay? So this kind of brings us to the rule of thumb formulation, is that non-adiabatic effects become important when electronic energies become comparable with the nuclear. And that also correlates with the statement, well, usually in all the textbooks they start with saying that nuclei are slower than electrons, right? And that's why we can separate them, right? What does that mean? In the energy language, slow means smaller energy gaps. And that follows from the following consideration, is that in quantum world, things are moving because they are in the superpositions, right, of eigenstates, because they are not in the eigenstate. Yeah, exactly. Eigenstates are stationary, right? So in order for you to move your system or test how fast or slow your system is, you need to put it in a superposition. And then if your function is in a superposition C1, say F1 plus C2 phi 2, right? And this, your Hamiltonian phi I, gives you energies phi I, right? And two systems are different. They have different Hamiltonians. The energy gap E1, say minus E2, is larger for one. So example would be two particles in a box. One box is narrow, another box is wide, right? So you have L1, which is, say, much larger than L2, right? And in the narrow box, the energy levels will be, the distance between the energy levels will be huge. The energy levels in the wide box will be kind of small, right? And then why is this important? Because if we study the psi square xt, then this is a kind of observable quantity, the probability density, and it will be proportional. The time part will be proportional to E of delta 1, 2 time divided by h bar. Right? So in this exponents, which will have also complex conjugated part. So after all, it's a cosine function of delta E1, 2, h bar, it's frequency of oscillation. Right? The frequency of oscillation will be bigger with a larger energy gap. Yeah?
So I've done all kinds of mathematical questions where they say, like, your particle has been arranged in this state. But physically, when you're setting up a state, like in reality, how do you set up a particle in a certain state? What is that?
Okay, so I'm not experimentalist, so I don't know exactly how to set up the particle in a particular state. My fantasy would be you wait for the particle to equilibrate, you cool it down to the ground state, and then you shine a laser, right, so that you pump the system into a particular state, and then, of course, laser will not depopulate the ground state, right? So it's usually what happens is that you're creating a superposition between the ground and some state.
Okay.
So you can pump, you can shine another laser pulse, and then you create the population, but there still will be population on the ground state and population on the excited state. You can do multiple pulses, and then you create all sorts of superposition or populations, and then you can work with that. Yeah. So, but more on that, I think Camille will tell us in the nonlinear spectroscopy, where they create all sorts of superpositions for the purpose of study system dynamics. Okay, but the main idea here is that whenever we talk slow and fast, it's in energy language, it's how far the energy eigenstates. Right? Because to get dynamics, you need to be in a superposition.
Okay.
Right?
Yeah.
And then the further they are away from each other, then the faster there will be oscillations. All right? Okay, so that's all for today, and we'll continue next time.